going to go ahead and get started because we have plenty of time and there's tons of stuff to cover. So, hello, everyone. Awesome. My name is Colt McAnlis. I'm a developer advocate working at Google on the Chrome Developer Relations team, and my primary focus is actually web games, which means that while the rest of Google is off trying to make the internet a better, faster, safer, more social place, I get to kind of go off in the corner and play video games all day. So it's a really tough life that I live. What I want to actually talk to you guys today about is a performance checklist for the mobile web. And everyone in the right classroom, right? You don't need to go down the hall if you're in Economics 101 or something, right? Fantastic. Before we get started, I want to point out this fantastic little hashtag down here. Perf matters. How many of you work in a situation where performance, the performance of your applications, matters to your company's bottom line and your job? If that's not every hand in this room, I'm going to tell you to get out. Fantastic. If you see something today that inspires you, a statistic you didn't know, something else that just makes you go, wow, that guy's not as bald as I thought he was, take to the interwebs, take to your social media, use the Perf Matters hashtag. It's a fantastic opportunity to socialize. Also below it, you'll actually see the shortened goo.gul, Google. Anyhow, that shortened URL is actually to the G+ web performance community. And don't worry, both of these will actually be on all of the slides, but the Google+ Web Performance Community is actually a great place. There's already a ton of very smart people there posting content about web performance. You'll see posts from guys like myself, from Steve, who gave the keynote this morning, Ilya Gregoric, Paul Lewis, tons of the big heavy hitters. So make sure you check that out and join, because it's a fantastic place, even though Google Reader isn't around anymore. So let's get started here. I gotta be honest with you guys. I actually pitched this talk a couple months ago, mainly because I was angry. I was super angry because this was the web that I was getting on my mobile device, just constantly. And it seemed like more and more and more, the websites I would go to would be trying to convince me to go and find their native version. Right? So I'd go to a website, listen guys, I just want to know if you guys are serving teriyaki chicken tonight. I don't want to download the native app for, Thai Bangkok Orchid restaurant down on Camden Street. Just tell me if you guys are serving good food. And so I realized after interviewing so many people and so many companies, like, why are you doing this? What is the reason? What is the plan? Is it engagement? It is all these other things? The number one thing they kept coming back to me is saying it's all about performance. That they tried to get the right application and the right experience for their users from their web app running on mobile inside of the browser, and they just couldn't do it. And I got angry about this, like Hulk angry. Like I flipped the desk and like Housewives in New Jersey. It was actually pretty funny the first time I failed. And then like someone came in and was like, no, you have to flip it this way. And anyhow, don't try to flip a desk without stretching first is what I'm getting at. Anyhow, the whole point of this was to come to a conclusion about, you know what, we actually can get the performance that you're looking for, but you have to look at it a different way. You see, any of you in here who've worked on multiple technology stacks know that what works on one platform doesn't always translate to the other platform. Right? I mean, memory models are different, call stacks are different, the amount of taxation that the underlying operating system takes away from you is completely different. You have to approach things with a different mental model. And what we're going to talk about today is the mental model and the checklist that you need to be embracing when attacking performance for mobile web. Now, the interesting thing about here is, and now everyone raised their hands, so this should be completely obvious to everyone. So let's talk about user truth, especially for mobile. So these statistics have been around a while, that 1 in 4 users, or depending on where you go to, 40% of the users who visit a site will abandon it or bounce if it's not loaded in 3 seconds. Everybody know that stat? It's a nice little haunting stat, right? If your company does what, $3 million a year in revenue because pages load and people buy stuff and, 1 in 4 are actually leaving because it's not loaded, that's tons and tons of money. Of that 47%, 80% of those people said that they would not come back to that mobile website. That's pretty haunting, right? So not only did you lose them the first time, you've lost a massive majority of them for every time after that. And here's the scary one. Of those 80% that said they would not come back, 50% of them said that they were very, very enthusiastic about telling their friends not to visit your website. The rage of these people, which is actually pretty interesting, right? So if your page doesn't load in 3 seconds, not only have you lost that user, but potentially all of their friends as well, right? This comes back to that little hashtag, performance matters. And it matters at every stage of it too, not just loading of web pages. So if you guys have actually watched the videos from Edge Conference London, which was back in February, anybody familiar with that one? Nobody. Awesome. New data, original content on the internet. So at Edge Conference, Facebook had a fantastic statistic. And they actually said, and you know, Facebook at the HTML5 conference, you know, obviously they have a lot of weight in that game as well. They said, hey, we ran a proposal. We actually took our native application, which was running at 60 frames a second, and we arbitrarily slowed it down, just to screw with our users. More importantly, they wanted to see how user engagement and attachment rate would fluctuate based upon the experience of the performance of their native application. Now, they were in a native app, so they could actually arbitrarily slow it down, so this was actually a pretty cool test. So here's what they actually found out, was that at 60 frames a second, everybody was happy, rainbows were flying through the world, everyone saw unicorns when they checked the like button. It was good times for everybody. When they artificially throttled it to 30 frames a second, they actually saw user engagement drop. They saw happiness drop, they saw user return rate drop. Most of the people would actually, they said they actually got a bunch of emails from people emailing Facebook and saying, hey, your app all of a sudden got slow, please fix it, I won't come back until you do. The shocking part of this was actually when they throttled it at a variable frame rate between 30 frames a second and 45 frames a second. At this point, they actually saw user engagement drop through the floor. They had people with pitchforks and torches and marching on the main building because it didn't feel smooth and it didn't feel right. What these two statistics actually tell us is something very important, that people are misusing the term web performance. Most of the time when you talk about web performance, you're just talking about this first statistic over here. How fast does your web page load? But obviously, it's not just about that. It's also about the experience that the user gets while using your application, which is also directly related to performance. So what we're going to talk about today then is that it's not just about network, but it's also about your compute performance while the user is using things, right? How your garbage collector is being managed, how long you're taking in your inner loops, how much are you touching your DOM for that matter, right? And it's also about render performance with all the fancy new stuff going on with GPU optimization, tiling, software rasterization, scrolling, and every other 50 buzzwords, right? You can actually get things very, very, very wrong by doing some simple CSS, which seems easy and should seem fast, but actually, you know, throws a wrench in your entire pipeline. So these are the three pillars of performance. From now on, anyone in this room, when you walk out of this room and you talk to someone about web performance, you will use these three terms, right? I love the random thumbs up. That's cool. I wanted a shirt that's just got a bunch of thumbs up. And it's like, I went to Colt's talk. So anyhow, let's get to this. Checklist. Let's start with network performance, because this is obviously the old school. So let's start at the top here. So why is the mobile internet a little bit slower than your desktop internet? Well, let's take a look at things here. If you have a mobile device, some random arbitrary device, I don't even know what form factor that is, and you have to ask yourself, how does this thing actually communicate to the internet and download all my wonderful pictures of cats? Well, of course, we already have an existing infrastructure of cell towers that have been in use for a lot of time. The funny thing is, your mobile device actually comes with this nice little piece of radio chip in there. And anytime you actually want to access your data, your phone will send data through the radio chip to communicate with the cell towers, which then actually goes to the intertubes, finds the cat, sends it back to your phone. So here's a really interesting thing, is because the fact that we're not using sort of modern technology, this stuff's been around a long time, we're limited on what types of data transmission rates we can get through these older towers. So of course, you know, most of America is actually sitting nicely on really fancy $500 phones and 3G internet, right? Well, 3G will actually do about 3 megabits per second at its max capacity. That's actually not what you get. You get 3 megabits per second when you're standing under the cell tower, right? Like bashing your phone against it, trying to download that new Rihanna song or something, right? To talk about that, so that'll actually download a 3-minute song in about 15 seconds, just to kind of put that in perspective. Now, to take a step back, when I connect to my neighbor's Wi-Fi, I actually get about 16 megabits per second. Right? Now, that's actually going through a concrete wall, a restraining order, and then another concrete wall. So obviously there's some ground that our mobile networks needs to make up. So if this isn't all, right, so you have to understand that as the users are pulling data off these wireless networks, it's obviously going to be a slower experience for them. But here's actually the kicker, is that that radio has 3 states. It's got active, pending, and idle. When that radio moves from idle to active, it takes about 1 to 2 seconds for it to turn on and negotiate transmission with the cellular network. Now, this should scare every single one of you in this room that you didn't know that, because I just showed you a slide that said if your web page doesn't load in 3 seconds, you lose 40% of your users. 2 seconds are gone if the user's radio isn't turned on. That means you got 1 second. Good luck. So you have to take this into account, especially when you're doing never-ending sites, delayed low content, infinite scrolling, right? These things very much matter on the fact that you're loading content over time. And if this radio goes into the idle mode, you have to pay that 2-second connection every time it pulls new data. If you're lucky, right, and only about 15 seconds elapse, then it'll just go in sort of the pending mode, and maybe you get half a second delay. But if, you know, they check their mail and then all of a sudden say hi to their friend, or, you know, watch Louisville beat Duke yesterday, which made me cry a little bit, you know, and then they go back to the phone, they got to pay that time again, which is not necessarily ideal. So this actually leads us to a huge big problem. Responsive design, anybody? Responsive design? Yes, lots of hands on there. We've got, what, 17,000 different resolutions that you have to make a mobile website for now, right? So the popular thing to go out and do is actually say, hey, let's do responsive design. We need to handle big images, small images, lots of resolutions, high DPI, low DPI, Androids, iPhones, smartphones, watches, shoes, and Google Knows, which was announced today as well, if everyone saw that April Fool's joke. So the problem with this is that you've got a lower band network, and people are actually just snapping pictures off their cameras and sharing them with each other through social networks and other sorts of things. So this image on the web right here is actually about a 1280 by 720. Very, very small by modern smartphone capture standards, right? Here's the interesting thing. If you actually just saved this, as most standard camera captures do, as a PNG, that's about 2.3 megs. Right? Now remember, with 3G standing under the cell tower, you get about 3 megabits per second. So obviously this is going to take some time to download. If you compress that with JPEG, it actually drops down to about 297K. Now this is fantastic, right? It's a fully opaque image. You don't need transparency data, so you actually get a lower resolution. But how many people in here have actually heard of the WebP standard? Right? So WebP is a new compression technology because people have actively stepped back and said, wait a minute, 60% of websites are made up of images, especially those going to mobile. We're spending tons and tons of time for users to download image data. Most of these pixels aren't needed or they're high resolution, but effectively you're downloading a 1280 by 720 image down to a small device and it doesn't need to happen. Interesting fact too, so actually before I came to Google, I actually spent about 10 years as a game developer. So I bounced around between studios that did lots of fun games that I won't mention here on camera, but you can find me afterwards. And one of the most important things we found were that human beings were really bad at compressing texture data. We would have an army of artists sitting in a room making textures to fit on a bullet, right? And this bullet would only occupy like 3 pixels of the screen, but they would have this huge 512 by 512 texture on it. Right? Like if you put that texture on the moon, you could see every little divot inside that bullet. And the thing was that, you know, they wanted the data there, they thought the data needed to be there, but it just wasn't needed. And then we found that we could compress 90% of the noise away, and the human eye wouldn't notice. In fact, if you actually look at this image, this is actually post-WebP compressed and upscaled about 4 times. Who noticed? Well, of course, there's a projector. You can blame it on the projector, but on the slides, it looks really cool. So the point here is that when most people are actually capturing about 5 megapixel images on their phones and uploading it up to the internet, you know, the size of your images has a huge toll with everything. Yeah. Number 2, this is actually a pretty simple fix. For any of you server programmers in here, you're just going to facepalm and go, OMG, I can't believe we're talking about this. But the fact is that your content is really too large, right? So with AT&T roaming rates inside of Europe as of today, may change in the future, their roaming rates charge about $19 per megabyte downloaded, right? Which means if you want to load Microsoft.com, that user actually has to pay AT&T $17 to load a home page. Here in America, we actually sit pretty well on nice prepaid plans with unlimited data, but when you start looking at these other cultures and how much they pay for internet access, you start to worry about what your page weight looks like. So let's say you actually have a 256K JS file, right, which is actually small. Again, 60% of your pages is mostly image data. Well, that getting transferred to every single mobile device is not necessarily ideal. It's actually pretty easy today with most modern web servers to enable some high data traffic protocols. For example, just turning on gzip compression, or actually turning on Speedy. How many people have messed with Speedy? Awesome, you my bros. Speedy. turning on gzip compression in Speedy is analogous to actually sending a 36K JavaScript file to these clients. Now again, you're sitting on a slower mobile network that's already dominated by image data that's oversized and overcompressed. Actually crunching these extra bytes out of your JavaScript files is pretty important, right? Because we should all be minimizing and obfuscating our JavaScript as much as we can to send it to the mobile web. We should be doing these things on the server side as well. And most of the time, they're just simple switches or simple configurations that you have to turn on that can actually yield huge and significant performance benefits for your users. So for those of you who are new to the network performance arena and would like to know more about it, there's actually some fantastic tools inside of Google Chrome and elsewhere to actually take a look at this. So if you have a hypothesis that the network is your problem for your users, I highly recommend stopping by the Chrome DevTools Network tab. Just load your site, take a look at what's going on. This is a fantastic little timeline view that will actually show you what assets are being loaded, how long it's taking to load them, and then how long it takes to actually process the data. More importantly, you can see how this scales over many devices, because hopefully everyone knows in here that all of Chrome DevTools actually work off of these Android devices. So you can actually load your site on your Android and actually do analysis on Chrome on your desktop, and actually see how your device is responding with the network conditions you have it set to. That's fantastic. If you want to dive a little bit deeper into technology stack, there's a great tool called PageSpeed. PageSpeed is an amazing suite of tools that will actually do some suggestive analysis for you. PageSpeed will actually, well, PageSpeed is kind of like your older brother who's a little bit a jerk to you, right? And he's like, yeah, that's a nice website, but how come you didn't compress that image 50%? I bet you could make a better website there. You know, or so basically it'll actually go through and actually do this analysis and tell you, hey, if you compress your images using a 40% reduction in PSNR, you can actually save about 50% in transfer time to your site. Or if you can compress your JavaScript more. Or here's some JavaScript function that you really shouldn't be loading anyhow. It's a fantastic little tool that you can do that will run suggestive analysis on your page. If that's a little too deep in the stack for you and you want to bubble up, you should definitely check out something called webpagetest.org. Hopefully everyone in here already knows about this. This is another fantastic site that will actually give your web page a grade. So you can actually go in there, type in your web page, and it'll actually give you grades. So actually, just to mess with Anne and the other people who run this conference, I actually typed in HTML5 Devcom schedule, and this is the results it got, right? So A, for first time to byte, this is how long it took the byte to get to the screen after initial request. Keep alive enabled compressed transfer, so they're actually using some data compressed transfer from the web, either gzip compression or Speedy, which is fantastic. They got a D in compressed images, so obviously they should go to actually try to compress their images a little bit more, maybe down-res them, and F on cache static content. So this means that they obviously weren't setting their cache headers to infinite or some other timeout. So this means that over time, the user would have to re-download a lot of this content. With these three tools, you can actually not only find where your problems are, find suggestions for improving it over time, and actually get to work immediately. So everyone in here who raised your hand that said performance matters to your job, this is going to increase your bonus next year. Good? Yeah. Thumb up. Get that guy a t-shirt. Peter, t-shirt. That's the bonus. I saved our company $20 billion, and all I got was this lousy t-shirt. So let's talk about rendering performance. So hopefully a lot of you are using really high-end web browsers on these mobile devices, which means that most of you will actually have a GPU path in your browser. Does anyone know that? Has anyone actually looked at that? Cool. New information on the internet. So what this means is that for those of you who don't understand how a web page is actually rasterized to screen, what happens is all of these little things that you specify in DOM and in CSS actually go through what's called a software rasterizer. What this is going to do is take your content defined in HTML and other portions and actually push each of the pixels into a separate bitmap. That bitmap is then going to be stored in memory, and with some paths, like the hardware accelerated path inside of Chrome, it'll actually push that data to the GPU. And then the GPU is actually responsible for rendering these bitmaps on screen. What this means, though, is that you actually have a software rasterizer running on the backside of your browser that's creating all this content and effectively touching this massive palette of pixels in memory. Here's the cool thing. All those CSS tags and properties that you're using to actually modify your page, they have implicit cost, or they have explicit cost that may not be implicitly noticeable to you. So for instance, I ran a little test. I said, hey, I want to know how much the paint times are for every single CSS property that exists. And so I wrote this really big harness that would spit out probably about 80,000 web pages. Each web page has a single DOM element with a single CSS property on it. Right? So with this, I can actually run through all these cool processes and figure out exactly how long a web browser was taking to paint each one of the CSS properties. It was haunting what I found. So first off, what you should notice is that the same property with different inputs can have drastically different performance. So what you're seeing here is box shadow. With 1 pixel actually performs medium, right? 1, 2, 3 black actually gives you the best performance. Why? I don't know. But if you put box shadow 1, 2, 3, 4, gives you horrible performance, right? Because something is going on under the hood. You have to remember, we're doing software rasterization, and some properties are easier to rasterize than others, right? Taking an image and blitting it to another image is actually pretty fast. But if you want to add an arbitrary drop shadow to a concave object, you know, paths have to be created, they have to be re-rasterized, they have to be clipped, they have to be alpha transparent gradientized, tons of stuff has to happen. What gets even more haunting about this is that when you actually start seeing that combinations of CSS properties have a non-linear time or nonlinear cost. So if you add box shadow and border radius stroke, both of these actually take about the same time if they were singular on the element. When you combine them together, you get a 3.2x increase. Right? So it's not just a linear thing. It's not just A plus B equals C. It's actually A plus B equals 3.2x or 3.2c or whatever. So this is actually really important, right? Because this means that you have to start evaluating what your page render weight is based upon how much time is being taken from your CSS property during the rasterization phase. If you'd like to go even deeper into the rabbit hole, who wants to go deeper in the rabbit hole? Yes! I want fireworks for you guys. Like, if you want to go deeper into the rabbit hole, how the hardware compositing inside of Chrome works is that it will actually dice up your web page into 256 by 256 tiles. And then it will actually render into each one of these 256 tiles and then store that in a CPU LRU cache. As you scroll vertically on your page, it'll actually run tons of heuristics evaluating memory footprint, overhead, time to fill those tiles, and actually you'll dump some out, right? So it actually keeps sort of a static memory footprint. And then it'll actually update to the GPU. So if you scroll to the bottom of your favorite Pinterest page, because there's a really awesome recipe for apple cider down there, and then you scroll all the way back to the top, chances are those original tiles aren't in the cache anymore and have to be re-rasterized, which means you're once again paying the additional overhead to re-rasterize those tiles. Gets pretty kooky after a while. Main point of this slide, understand what your page's render weight is moving forward. The trouble with images, part 2. So this is the same image that you guys saw before. It's fantastic. And this is the device that you're sending it to, right? That's not cool, right? You're sending this nice high-resolution image that's actually showing up on a very small screen. Obviously, we talked about this before, responsive web design. But here, do you understand why that's actually a problem? It's not just a problem for network bandwidth. You actually get double taxed when you send images that are too large. Let's take a look at this. So this is actually a timeline that was captured during rendering of one of these tiles that I was talking about a couple minutes ago. So what you're seeing here is this is actually a frame. So 3 images were on the screen. One of them was small, one of them was super large, and then one of them was medium-sized, okay? All of these images were dynamically resized to 128 pixels by 128 pixels. This big bar here is the scariest thing I've seen in my 10 years of professional performance development. This is 51 milliseconds to decode that image. So that 51 milliseconds is not small, right? If you consider your page needs to be running at 60 frames per second, that means you get 16 milliseconds per frame while the user's moving their mouse around, right? At 51 milliseconds, you just blew about 4 to 5 frames. Here's the cool part. After you've decoded this monster 1680 by 1050 image, you have to spend an additional 29 milliseconds to resize it down to 128 by 128. And again, this happens every time that tile that the image is touching has to be re-rasterized. In contrast, you can see that this image that's actually half resolution of the one up there only takes 22 milliseconds. So you're going from 80 milliseconds to decode and resize an image, when if you actually made it closer to the standard native resolution, it only takes 22 milliseconds. Yeah, that's kind of haunting, right? Anybody haunting? No? I see 3 people asleep. I'm going to wake you up. Number 3 here. So if image repaints and sizes and all this stuff wasn't haunting enough for you, let's talk about reflows. Again, we all come back to dynamic response, right? Because everyone says, hey, I only want to write my code once and have it run everywhere here on the internet. So I want to do things right. So let's take a look at this code. Seems pretty innocent enough, right? So at the top, we're actually getting some container divs, and then we're actually going through and getting some children dividers that will be existing inside of that. And then we're going through for each of our child objects and setting its width equal to its parent container.width, right? Seems pretty innocent, right? You just kind of resize your thing, everything matches in there. Well, what's actually going on is that this is one of the worst performing pieces of JavaScript code that you can write, okay? Here's why. Every time you modify the property of the DOM, you cannot read from that DOM until everything's been recalculated. Because you may inadvertently change something which modifies the position, rotation, or timing of something else on your web page. So what's going on here, so once you actually write to style.width, okay, it'll actually set a dirty bit on the DOM. The next time you attempt to read any property from any element that's in the DOM, it says, hold up, brother, I got to go recalculate some stuff. It'll run off in the corner and actually spend some unknown amount of time, 5 milliseconds, 15 milliseconds, 30 milliseconds. You don't really control that since it's based upon the size of your DOM and the complexity of your DOM. And then it'll come back to you and actually give you that 2-pixel value that you actually wanted in the first place. So what's actually going on right here is that you're actually doing an initial read from container.offsetWidth, and then you're doing a write into style.width. When that loop comes back around, you're going to try to read again. It's going to go, oh, hold on, got to go reflow. Come back, write. You're going to come back around through the loop. Hold up, got to go reflow. And so what happens is for every single object inside of this DOM that you want to touch, you're going to pay the cost of going off and recalculating where everything in the DOM is. And for those of you in here who are actually writing large, infinite scrolling, delayed loading websites, this can actually destroy your performance more than anything. A better way to look at this is actually to batch or cache this data out, right? So instead, what if we actually queried container.offsetWidth once, and then we actually went and assigned it after that? Now this is fine, because what we've effectively done is we've read the value and then gone right. And then when this frame is over, when the DOM comes back around and actually needs to be rasterized for whatever tile, you'll actually pay the toll or the taxation to configure the DOM positions at that point in time, not during your high-performance JavaScript code. So making sure that you're modifying your code and understanding where everything is coming from is critically important to minimize these DOM reflows. Tooling. So for those of you who think that your problem is in the compute layer, there's 2 amazing tools that I can't spend enough time ranting about. First off, open up a new tab in Chrome and type in Chrome://tracing. There's going to be a big fat button that comes up, and you're going to hit record. And then you're going to go to your website, and you're going to do some stuff, and you're going to come back to that tab, and you're going to hit stop. And what you're going to see is a timeline, like the one I showed you before and the one you're seeing now, that actually shows you where all of the processing time inside of Chrome is going from what your web page is doing. So you can actually see how long that oversized image is actually taking away from your frame time, right? Another one is actually the DevTools timeline. This is really cool because the DevTools timeline, as everyone in here should hopefully know, will actually show you where your paints are occurring. And it'll actually, if you hover over it, will show you what part of the page was actually invalidated that caused that paint to occur. So with these 2 together, you can actually see where you're sort of creating these sins and taking too much time away for rendering, and then also see what part of the page was causing that. So between these 2, you actually get a good insight into everything. Compute performance. This is actually my favorite part. I'm a compute performance guy at heart. If you can ask Ann in the back out there. If you guys ever see my Udacity class on HTML5 game development, I constantly rant about how performant runtime code is the most important thing you can do. Beyond anything else, if you treat the runtime code correct, it just kind of trickles out through the rest of your mental model. So this is I'm just going to rant a little bit. So has anyone ever had a memory profile that looks like this? I see the couple hands that went up were like, yeah, hopefully my boss doesn't know I'm here. So what you're actually looking here is at a memory profile. Now, JavaScript is a garbage collected language, which is fantastic for you programmers who don't want to free your data because you set it to null, and then sometime in the future, magical fairies show up inside of the virtual machine, free your data, and then you continue on. Well, the problem is each one of those dips there in the overall memory is actually where the garbage collector is running. Now, the garbage collector can be invoked anytime JavaScript is executing. So this means it can occur inside of a mouse move, an on-click event, inside of a RAF, inside of a WebSocket receive. Anytime JavaScript is executing, it can halt, and then the garbage collector can run off for 35 milliseconds, completely screwing up your 16 frames per second time, right? Your goal should not be to have a memory profile that looks like this. Your goal So this is actually captured over 4 seconds, and you're actually seeing that we're losing 23 milliseconds. So that's about 2 frames of time during that where you're getting these stutters. Your goal should have a memory profile that looks like this. Now here's the interesting thing, is that all of you in here have some understanding of what the upper limits are for your application. Even those of you in here who are writing infinite scrolling, infinite loaded, delayed loaded applications have some mental model about how many things you can realistically do on your client. If you know that number, that there is no reason then you should have dynamic spikes in your memory where the garbage collector is taking a lot of time. Instead, you should actually be pre-allocating those objects, like you're seeing on the bottom here, and moving towards static memory JavaScript. Right? Anyone know Emscripten? Emscripten's a really cool technology that'll actually take C++ code, compile it with a Clang compiler through LLVM, and actually generate JavaScript from that. That JavaScript can actually just be loaded right into your DOM and executed. And it's actually running amazingly fast. You're actually seeing some C++ games running at 30 frames a second inside of HTML5 because it was cross-compiled from C++ through LLVM and into JavaScript. The key to Emscripten actually making these performance gains is that it takes an assumption of zero or static memory JavaScript. What it'll actually do is actually pre-allocate a massive binary typed array, and then it emulates all of the standard assembly level operations that are coming in from LLVM. So it doesn't allocate any new memory at all. It completely gets rid of the ability for the garbage collector to take any time away from it by effectively assuming itself as another VM on top of a VM inside of a web browser. But it works, and that's what's important. So here's an interesting poll for you guys. So some other innocent code that we have running here. So let's say we've got object equals new object, and we've got a list where we create a contiguous array of 100 elements, and then we call array.add. How many people in here know what happens under the hood? Because we have 100 contiguous elements, right? So you would think that maybe you would add one more, but it's supposed to be a contiguous array. Interesting enough, what happens under the hood inside of the JavaScript VM is actually what you would see in other native applications. If you run C++ code and you do the same thing, you'll get the same performance. What happens is, instead of actually appending this at the end, inside of the code, it'll actually resize the array by creating a brand new array of double the size. So if you got 100 elements, it'll create a 200 element array. Here's where it gets awesome. It'll then copy all of your object references from your original array into the new array, and then change the references so that you're now pointing at this new 200 element array under the hood. Doesn't sound that bad, but what happens when you get to 201 elements? Or 401 elements? What actually starts happening under the hood is you start adding these items in here, you get an exponential growth of memory that's just being taken up. Not to mention, every time that array resizes, you now have a huge collection of objects that the garbage collector has to go back through and touch. Right? So if you don't understand your native footprint and don't actually pre-allocate for it, you're actually running into this scenario where you're just burning tons and tons of processing time and garbage collector time because you're just unknowingly creating objects. What you should be doing instead is know your growth rate. Right? Again, you should understand, run your application 900, 1,000 times. Print out the max number of elements or the max number of types that you're actually using. Right? This should give you an understanding of a max footprint. Once you have a max footprint, pre-allocate that number of objects. Start there. Right? There is no reason, really, for any of you in this room who are writing applications to ever have to resize an array during your JavaScript web performance application. It shouldn't exist. Right? Even for those of you who are doing awesomely amazing infinite scrolling. Know your growth rate, know your Mac footprint, and pre-allocate to that as much as possible. Now, for those of you truly bald and aggressive and disgruntled in the audience, hands up, bald and disgruntled. You're not bald. No, no. Take his shirt. You're not bald either. Anyhow, for those of you who would like to dive deep into the belly of the dragon and see the sort of stuff that we work with all day on the performance team over at Chrome DevRel, there's two fantastic tools you should be looking into. The first one is actually the DevTools CPU profile. So you've opened up DevTools inside of Chrome and take a CPU snapshot. It'll actually show you where all of the performance for that snapshot has gone. Right? So it'll actually tell you that if you look at this, that 75% of your time was actually, or 23% of your time was actually in animate. Right? This means that's where the bulk of your time is actually going. If you'd like to take a step further, you can actually also in that same tab take a memory heap snapshot. Now the memory heap snapshot is a little bit weird, but it'll actually show you the type of all of the objects that are still existing on your page. And there's this really cool feature where if you take a snapshot, wait a couple seconds, and take a secondary snapshot, you can change it to tell you and report only the objects that have been allocated between the two snapshots. So you can actually see your delta over time. This is cool because it actually tells you how many objects you're leaking, how many objects you're creating, and what your overall memory churn is. Remember, the whole goal here is to reduce the ability for the garbage collector to run and screw up your ability to actually hit a true 16 frames a second for your user. So I'm actually finishing a little early. That's OK. I saw some hands go up while I was talking, so hopefully we'll have tons and tons of questions. So here's your checklist. Number 1, use advanced data compression for image transfer. If you haven't checked out WebP yet, go check it out. There's a fantastic client-side hint proposal that goes along with it from Ilya Grigorik. I highly recommend you take a look at that. Number 2, use proper transfer protocols for fastest possible speeds. Make sure that you're using server-side compression, gzip, speedy. Take a look at these technologies, understand them. Know that flipping a couple bits can actually save your users a ton of money and you a ton of money as well. Number 3, batch your network connections through the radio. Remember, every time that radio goes idle, you're going to pay 1 to 2 second cost to reactivate it. So you got 2 options here. Number 1, keep transferring data, or number 2, grab as much data as you can and let that thing turn off, and then don't touch it unless you absolutely need it sometime in the future. That, by the way, for those of you who are actually concerned about battery life for these mobile devices, that's actually the #1 thing you could do. There was actually a funny story. The guys who made PhoneGap tried to add an API in there that would actually tell you what the battery life was, right? But it turns out actually calling the API to figure out what the battery life was cost 3x what it should have reported in terms of battery life. So like they would call this API like 12 times and the battery would disappear, right? So battery matters in this stuff. That's a different hashtag. We have perf matters, battery matters is a different hashtag. Focus on reducing your page render weight. Understand what your CSS properties are taking from you in terms to actually rasterize your page. This is probably one of the most important things I think web developers need to come to terms with, is that your general browser is not a magical utopia of unicorns and pixie elves, right? It's actually highly, highly modified, aggressively optimized C++ code that's running a virtual machine, a network stack, and tons of other stuff that none of us know about, right? You have to understand that anything you do inside of JavaScript and inside of your DOM have ramifications in that world, and your page render weight is one of them. Reduce your image resize times by scaling down your images for mobile. Yes, it is a pain, but guess what? That pain is worth it because it's going to reduce how much you're paying to send those images, right? I think if you look at the latest CDN transfer rates, if you actually have a scalable network, it can cost you hundreds of thousands of dollars to send images that are way too big for your mobile devices. Batch your reads and writes to the DOMs. Reflows are the devil. Stay away from them. Just try to avoid them. Batch your reads, then do your writes. And then make sure that you move towards static memory usage patterns. This is really, really important because you want to reduce the ability for the garbage collector to tax you over time and take away all that 16 milliseconds you need. So with that, I am done. A couple resources for you guys here if you haven't already seen them. DevTools debugging on Android Chrome. If you do not know how to set up DevTools debugging for your Android devices, visit that URL right there. This will change your development life. And also, there's a great thing on capturing a trace capture. So if you actually want to do about tracing on your phone, that second URL has a fancy little Python script you can run, which will do all of that for you. For that, please follow me on your social media network of choice. Give me emails, and I believe that's it for me now. Let's open the floor to questions. Thank you. Great question. So other techniques and strategies for pre-allocating with your app, because you don't always know how AngularJS is using memory or jQuery or anything else. Yeah, so that's a little tricky. First off, you should be sending those guys emails and asking them what's going on, right? Put pressure on the people who are doing that. Number 2, though, is sometimes pre-allocation doesn't always work, right? Sometimes you hit that limit and you're just going to expire it. Like dynamic stuff happens. For that, I actually recommend a data structure type. So instead of actually using a standard JavaScript array, I actually recommend using something called a linear growth array. So effectively, you write this nice little framework that every time you exceed the current capacity of your JavaScript array, instead of exponentially growing, you go under the hood and actually create a smaller known size contiguous array. So instead of actually doubling in size, you may only create 100 new elements each time. Right? So this means that your growth is never exponential. It's actually O to the 1 of 100 elements each time. right? And then when you start doing some crazy stuff like slicing and removing, things get a little crazy. But at least you know that your upper... My phone told me I was wrong. But at least you know what your growth rate pattern is at that point.
Do you have tips for making the JavaScript engine behave in a more static memory manner?
Say that again, I'm sorry?
So you mentioned using more static memory. Do you have tips for manipulating the JavaScript engines to do that?
Yeah, so object pools is another big one. Anyone object pools? A couple people, fantastic. Wow, it's like a treasure trove of awesomeness in here. So object pools are this fantastic data structure that effectively, instead of going back to the JavaScript heap to allocate a new object, you instead allocate a bunch of them over ahead of time, like let's say 90 DOM elements or something, and then you put them in a pool. And instead of actually going to the heap to grab it, you actually go grab it from this pool and use it. And then when you're ready to get rid of it, instead of actually setting it to null, you push it back into the object pool. And so what happens is, over time, is that your actual memory allocation growth rate will actually go to 0, because you're going to hit that max limit, and you're never actually going to hit the heap to grab more data. You're just going to constantly be grabbing it from your free pool. And of course, that's just a linked list or doubly linked list or even a contiguous linear growth array. But this is actually one of the really important things, because when you couple linear growth array plus object pools and the mental model of you're trying to get to static memory JavaScript, you can't lose. Right? This gives you all the data that you need to actually get there.
Do you know of any resources that we could go look at for these sort of memory management techniques?
Unfortunately, there aren't a lot of good ones right now. I have 6 blogs in my queue right now that I'm hopefully to put out this quarter. So keep your eyes on H5R Rocks for this quarter. And we will also be talking about this at Google I/O a little later this quarter, and also on my blog as well. Unfortunately, there's not a lot of good stuff out there, because some of these techniques actually come from C++ land and native application land, and anytime I come to a web developer and I'm like, you should do that like we do it in C++, like I have to get my hands up really quick before their axe comes down. So unfortunately, there's not a lot of good documentation.
Okay. So you mentioned some problem with the array implementation and things like the garbage collector. Don't you think that the browser or the VA engine could do a better job optimizing it instead of us having to change our code?
Oh, the definitive argument for web technologies. So I only heard a couple pieces. So your question was, don't you think the V8 and the browser should do a better job of optimizing memory instead of us doing it ourselves?
Yeah, like for example, a better garbage collector that doesn't lost.
Yeah, so V8's garbage collector is top notch, period. I've played with them all, Java, C#, all of them, right? V8 is actually pretty much one of the best ones out there. It has an incremental model, so what will happen is it'll actually free data in multiple phases of how old it is, right? So you never actually get one big punch, you actually get gradual punches over time, but you're still losing that memory over time, constantly. This is the ebb and flow of a garbage collector, right? Effectively, you have to think of it this way, is you're paying a tax. Your tax is, like, I would like to not have to care about memory, and what you're paying for that is 15 milliseconds sometime in the future. What's missing from a garbage collector, and this is my personal opinion, not that of any representative companies, organizations, or secret societies that I may or may not be involved with at any time in the future. Okay, PR and legal is happy. So one of the big problems, though, with garbage collected and managed memory environments is that it misses intent. Right? You're the programmer, you know what your application is trying to do, you know the goal that you have in hand. This is all context that you have in your hand, and in JavaScript, we have absolutely no way to hint to the underlying virtual machine or the underlying garbage collector about what our intent is. Right? So you can't tell the garbage collector to do anything specific or say, hey, I'm about to go idle for 15 milliseconds, so if you'd like to go run your garbage collector, now would be a great time. We don't have that ability. So because we lack the APIs and the control to change these things, we have to resort back to actually doing things manually. Who knows, maybe in JavaScript 7 or HTML5 9 or HTML9 or whatever, we may get some of these controls. Until then, we have to attack this with solid computer science understanding. Right? Nothing that I've presented today isn't taught in computer science undergrad. Right? I mean, we're talking about data structures. We're talking about batching, culling. We're talking about moving your hotspots to different locations, understanding your underlying architecture. This is all standard computer science techniques. We just have to take that viewpoint when we're looking at web development, because right now we're kind of caught up, in personal opinion, we're kind of caught up in this dogma that everything should be handled under the hood for us, and that's actually leading us into some very dangerous places, because it means that we're not allowing ourselves to hint to the VM. It means we're not allowing the garbage collector to get better. Instead, we're telling the garbage collector, hey, go look at my code harder to figure out what I mean. Again, personal opinion, not that of any representative body or organization or secret society I may or may not be associated with.
All right, just to add to the gentleman's question,
yeah.
I just want to put out there also that there are people still getting PhDs for garbage collection at this time.
Yes, absolutely.
And they will be for the next 10 to 20 years.
Absolutely.
Garbage collection is not a trivial subject.
Oh, no. There's a great book, in fact. If you actually go get Garbage Collection, The Definitive Guide, it's a fantastic book. In fact, I actually just posted a great book list on my G+. Go look at that book list. Garbage Collection is on there. It will blow your mind. It's amazing to see what these things do, and I'm highly happy to have it going.
All right, to my question here is, the beginning there you presented some really awesome examples of metrics that we should be looking at when developing our web pages. And of course, because of the talk, you don't have time to share everything with us. Do you have others that are posted on your blogs or other places that we can, because I can't read everything that comes out in the news source, so can you address that in a bit?
Standing right here, the best thing I can tell you to look at is follow Steve, who gave the keynote talk this morning. Follow Ilya Grigorik, fantastic guy. Join the Google Plus web performance community. I'll go back a slide so you can see that. Join that little short link URL there. Follow Perf Matters. There is not a really good community for web performance right now.
The reason I was asking this because I was considering doing the exact same talk that you just did.
Yes.
And I know because I've talked to hundreds of developers and they're all under this illusion that we'll just throw some more CPUs on the back end and we'll fix this, and that ain't going to happen. So thank you for doing the talk first, and put something on your blog that tells us where to get all this other stuff too, please.
Will do.
Thank you.
Thank you.
Okay, so the question deals with dev tools, and it's like connections like Android Chrome. So
okay.
I've been using that recently, and I love it. But the thing is that, okay, usually my problems are not with the kind of Android Chrome, but the other WebKits. Any chances of kind of like connecting the same tool or the similar tools for like being able to really do memory profiling on, say, I don't know, iOS, maybe some other WebKits too?
So I don't know about that, because everyone's proprietary technology stack has the stuff that they view as the right way to view the world. I will say this, though. If you actually go look at the Chromium source code, inside of the tools directory, there's a great little library called Telemetry. And Telemetry is a nice little automation framework that actually built a lot of my CSS paint timing on top of. Telemetry is actually kind of intended to be browser agnostic. It's sort of like a front-end continuous integration setup. So you can actually say, like, hey, go launch every browser on every device that happens to have a USB connection to this machine, and then load this web page and do some analysis through DevTools communication there. So if we're going to grow as a web performance community moving forward, I would hope that it would start with something like that, because right now it's too hard to do testing on 900 devices, right?
Okay, we'll have a look. Thanks.
Thanks.
You made a great sales pitch for WebP format.
Awesome.
Yeah, but
Thank
the
you.
problem with it is Chrome's the only one that uses it. So what is your recommendation then for our friends in IE and Firefox still?
Great question. So WebP is awesome. Great sales pitch. Thank you. I worked hard on it. What do we do for other browsers? So there's a couple problems with WebP and the fact that it's only supported in one browser right now. So the first thing is everyone in here as developers should be talking to whatever representative you have at every browser and beating on their door for a better compression format for images. Even if it's not WebP, just ask for something better. I mean, God, the amount of bytes that we're losing and the amount of money it's costing us is really just embarrassing. I mean, we've solved all of these other problems. Hell, at Google, we got cars that drive themselves. We should have a better, image compression format that runs around. So number two is, if you're actually in the situation and you want to adopt WebP, there's a couple things you need. First off is you need some sort of client-side hint to your server-side compute, right? Because eventually you're going to get to a point and you're going to say, hey, you're not running IE, or you're not running Chrome, you're running IE, and use a different set of data, right? that has a great proposal by Ilya Grigorik. Again, Ilya is an awesome guy. I work with him. He actually has a set of code on his GitHub account, as well as a proposal that he's trying to push through the standards bodies to actually introduce this as something that the web development community moves forward on. So basically, right now, what you have to do is you have to say, hey, if you're running in Chrome, we can save you a lot of bytes and a lot of time, and it's going to cost you less money as a developer and a lot less money for the person using it. And then you've got sort of these permutations for other browsers. Unfortunately, that's kind of where we're at.
So it's not just a WebKit thing, it's actually just purely Chrome.
I believe so right now, although is Steve still in here? Steve? No, Steve left. Good. That's probably a good thing. I believe right now it is Chrome only. Yeah.
Okay.
Yeah.
Thanks.
Hi. So I batched my questions to be efficient.
Okay.
I have 3. So the first question is, if you do our own heap management.
Say that again?
If we do our own heap management or our own garbage collection,
Yep.
Like you mentioned, do you find that you're spending a lot of time nullifying objects, like clearing stale data, resetting the objects to empty?
Okay, so there's 3 questions. We'll answer that one first. So everything you do with a performant application should be validated by performance analysis. Right? So I can stand up here and give you a fine checklist, but you should not adopt anything I've said unless you've proven with your own analysis that it's worth the time. If your memory growth never goes above 200 items, there's no reason to adopt any of this, right? But if you're dealing with the high performance stuff, the stuff that's taking 900, 1,000 DOM elements that are getting touched with text nodes, image nodes, all this craziness, your memory is jumping up to 180 megs per frame, things along these lines, you need to go and take a look at this. And I bet you'll find, and this is what we found in native coding for years, and we're now starting to see it trickle into the internet, is that managing your memory results in better performance. So that means the overhead of managing it is still going to give you a win.
You also mentioned that we should batch our network connections to optimize on the radio connection time. What are the techniques for that?
Great question. So this is, again, so web performance as a community is still budding. We haven't had a lot of solutions for this, right? So my view of web development over the past 15 years has been designers have said, let's make it more awesome. And then we made it more awesome, and it's like, oh crap, it runs slow. And we're kind of backpedaling now, trying to fill in all the gaps. And unfortunately, we've got standards bodies that are in the way to change all these things now. And plus, browsers all disagree on the way to do it. So I would say this is that the best thing you can do is judge and prefetch. Right? So if you know that 15 tweets are going to come through or 100 tweets are going to come through, either, again, fetch them in increments, pull them down, save them in a cache, right? Try to grab maybe a 6 megabyte block of data, push it into a cache, only show the user 15K at a time. Make sure, I know that there's a great talk out there by Jake Archibald about app cache and how people feel about that, but definitely taking advantage of app cache, offline storage. These types of things will allow you to actually cache data, so you're doing more of the management of your data churn on the client device as opposed to continuously hitting the network toll. So again, try to grab a big block of data, cycle through it on the backside. And if you can, try to do sort of an overlaid I/O model, right? So if you can actually do rendering and network traffic, right? So if you can prefetch, so let's say you grab a 6 megabyte block, you save it to disk, you're showing the user 1K blocks of data, and you get about halfway through that, and you actually kick off your next network connection to grab a 6K block. Well, the cool thing is that you haven't actually eaten up your initial 6 meg block, and your next 6 meg block comes in, so you can actually just stream through, and it's a continuous, seamless experience for the user. This is not new to JavaScript. It's not new to web dev. It's been around for 20 years of stream computing, and so adopting those principles to how we're doing our web pages is really ideal.
Last question. Is there a way to know what the connection type is, so whether you're on a 3G or a Wi-Fi network, so you can give a different experience?
You're preaching to the choir there, brother. Unfortunately, I don't know of a proper thing to do this. Usually what a lot of the networks will, or a lot of developers I've talked to will do is much like speedtest.net. It'll send a quick packet back and forth and try to estimate time. Usually that round trip time is fast enough to get a detailed information to understand what type of resolution and asset load and render weight you should send down to the client. Unfortunately, we don't have a good solution right now.
Thank you.
Thank you. Okay. All right. Hey, thank you for your time, everybody. Appreciate it.